Hi guys, Mr. Markwick here. Today's video we're going to be looking at transition matrices. Transition matrices are good as they help us model how a system changes over time. For example, transition matrices can be used to look at how a population may change over time. Transition matrices can be used to look at how consumer habits change over time in terms of what products they're purchasing. And then we could also look at how an advertising campaign, for example, may change those habits over time and therefore change the transition matrices as well. But that's something we'll look at in a separate video. Today was more of an introduction to the idea of transition matrices. The example that I'm going to go through here, before I go through a more detailed example, the second half of this video involves an ice cream brand called Ace. And they currently have 63% of the market. And this is represented in a state matrix here, or the initial state matrix. Now, a state matrix will tell us basically the state of things at any particular time. S0 is the initial state matrix. So initially, the market for Ace is, well, Ace has 63% of the market represented there as a decimal, 0.63, which means that the other brands have 37% of the market, again represented as a decimal, 0.37. I'll just point out with state matrices, these can show proportions like they are right now in terms of percentage, but they can also show actual values. So they might actually say, there are 1,000 ice cream purchases at a particular store, and 630 of those purchase Ace and the rest purchase other brands. That could be a state matrix to start with, okay? But in this case, we're looking at proportions in terms of percentage. So 63% for Ace and 37% for the rest or other brands. Now, Ace has looked at the market and how things change from week to week, and they've found that people that buy Ace now, of those, 80% will buy Ace again next week, and 20% will buy another brand next week. Of those who don't buy Ace, so they buy another brand, 30% of those will buy Ace next week, and 70% of those will continue to buy another brand next week. So that's represented in this table here, okay? Now notice again that these percentages have been converted to decimals. In a transition matrix, these do represent proportions. Transition matrix will always have rows that add up to 1, representing 100% of, in this case, consumers. So Ace, if they buy Ace this week, 80% will buy Ace again next week. If they buy Ace this week, 20% of those would choose to buy another brand next week. Again, that adds up to 100%, or this decimal will add up to 1. And you can see the second row also adds up to 1. So that's just converted to a simple matrix down here. You can see the values are the same. And this transition matrix, helps us determine what's going to happen on a weekly basis in terms of change from that initial state matrix. Now, what we're going to do is we're going to use the initial state matrix and the transition matrix to determine what percent of the market Ace will have in 1, 2, 3, 4, and 5 weeks' time. Okay, so in order to do that, what we're just doing is we're finding the product of the initial state matrix and the transition matrix that we're given. So it's simply in 1 week's time, S0, the initial state matrix, times by T. Okay, and that will tell me the proportion of the market that Ace and the other brands have in 1 week's time, based on this modeling. Okay, so on my graphics calculator, I'm going to do this. I'm just going to put in the initial state matrix here, which is a 1 by 2 matrix, so 1 row and 2 columns. Okay, and it's 0.63 and 0.37. And then I'm going to multiply that by my transition matrix, which is a 2 by 2, so 2 rows and 2 columns. So 0.8, 0.2, 0.3, and 0.7. Okay, So multiplying those together, I get the answer 0.615 and 0.385. What I'm going to do is just take a screenshot of that and stick it in our solutions here. So what it's basically telling me is that, whoops, it's really big, it's really small. In 1 week's time, the market will look like this. 61.5% of the market will still belong to Ace, and 38.5% of the market will belong to the other brands, okay? Now you can see that that's actually a decrease. So what's happened after 1 week, the market, which was initially 63% purchasing Ace, has now reduced to 61.5%. And obviously then the other brand market share has increased from 37% to 38.5%, okay? After 2 weeks, how do we determine the, in this case, the market share? We're going to use the initial state matrix, multiply it by the transition matrix squared, okay? Or we could have just done this, multiplied it, the initial state matrix multiplied by the transition matrix, and then multiplied that by the transition matrix again, which is still going to give us the initial state matrix multiplied by the transition matrix squared. Okay, so on my graphics calculator, again, I'll determine what that is equal to. And all I'm going to try and do here, this is a little bit of a shortcut, is just square my last equation, which will give me, again, a slightly different answer. Again, I'm going to screenshot this to save the hassle of writing it down. So you can see there, in this instance, that the, that now the market for Ace has decreased further to 60.75, and the market for other brands has increased further to 39.25%. Okay, for the state of the market after 3 weeks, you guessed it, we're doing the initial state matrix multiplied by the transition matrix cubed to the power of 3 for 3 weeks' time. Okay, so that will then equal, on my graphics calculator, something different. So I'm just going to change that squared value to cubed value, or to the power of 3. Again, I'm just going to screenshot that solution. So, and they're getting really big, these screenshots, aren't they, these days? What's happened? Anyway. That's more manageable. All right, so again, you can see that the market share for Ace is decreasing again. It's gone from 60.75 after 2 weeks to 60.375 after 3 weeks. Again, I'm going to do the same thing for 4 and 5 weeks. And yes, it is the initial state matrix multiplied by the transition matrix to the power of 4 for 4 weeks, and the initial state matrix times by the transition matrix to the power of 5 to see the market share after 5 weeks. So again, on my graphics calculator, I'm just going to go back and change those values at the end of the transition matrix from cubed to the power of 4. And then after this, I'll change that to the power of 5. So you can see again, it is decreasing, but it's starting to slow down a little bit. It's not decreasing by as much. And that's what we're sort of going to, that's kind of why I'm repeating this a little bit. So apologies for that. But there is a purpose for me repeating this. I guess I want to show you, I'll do it one more time. So this time to the power of 5. you can see here there's really not much change at all between the market share at or after 4 weeks and now after 5 weeks. Okay, so what's kind of happening here is we're getting to a point where the proportion, in this case, of the market or the number is not changing too much. We're getting to what we call a steady state. Okay, so this is 60.1. This is 60, if I round up, 60.1% again, 39.8%, 39.9%. So there's really not that much change at all. So what happens after a while is we'll get to a steady state where the proportion of customers that purchase ACE and the proportion of customers that purchase other brands will not change much from week to week. We call that the steady state. Okay, so we've just sort of gone through this first part here. Given an initial state matrix of S0 and a transition matrix T, multiplying them together, the state of the matrix, so the state of the system after any number of weeks, let's say n weeks, is represented by the equation Sn equals the initial state matrix multiplied by the transition matrix to the power of T. Okay, so like we said, after 5 weeks, we're just putting in T to the power of 5 to find out what the state of the market in this example will be after 5 weeks. Okay, so we saw there was little change from 4 to 5 weeks. They are converging to 60% and 40%, 60% for ACE and 40% for other brands. So like we said, we say it's reaching a steady state. Now there's 2 ways to find the steady state of a system. First, we can continue doing what we were doing from week to week, okay, by increasing that value of n, I guess, so to speak, the index number there, continuing to increase it and multiplying it by the initial state matrix. Or we could just look at the transition matrix to a power of a large number, okay? So just putting in a larger number for the index of the transition matrix and seeing where that takes us, all right? Just a couple of things to understand here around that is that if we use the first method, the steady state will either be actual amounts or proportions, depending on what the initial steady state matrix is actually giving you. In this case, remember, it is giving us a proportion, but I did go through an example, like let's say it was 1,000 people, 630 people buy ACE, 370 people buy other brands. In that case, it would give you an actual number, okay, with that continued multiplication or, method 1 here. The second method, just trying to find a large number for n, raising that transition matrix to a larger power, that will always be in a proportion, okay? Because remember, the transition matrix is always in a proportion in terms of percentages, and the rows will always add up to 1, okay? But what we're looking for really to find that steady state when we're using that second method is when the first row and the second row are pretty much identical, okay? So if I looked at this transition matrix, again, let's pop it back into the graphics calculator. It's a 2 by 2. And we put in, say, for example, 0.8, 0.2. And, oops, sorry. I didn't put that in properly. Let's try again. 0.8 and 0.2. And then 0.3 and 0.7. Based on that example. Now let's raise it to, like, say, for example, the power of 10. Okay, you can see that, again, like this value here, or these 2 values here in the first column are very close to 0.6, and these values here in the second column are very close to 0.4. Like I said, they're converging to, 60% and 40% respectively. Let's try that again. But let's change that 10 to 20. Okay. And again, you can see that like it is very, very, like if we rounded it, almost identical. So I would say the steady state for this transition matrix is 60% and 40%, meaning 60% of the market will belong to Ace and 40% of the market will belong to the other brands. Okay, so that's something to consider in terms of working out steady state when those two rows are pretty much identical. Okay, and in this case, to 5 decimal places, they are, or at least what I consider 4 decimal places. Okay, so that's a bit of an introduction. If that helps and you're ready to do a question, fantastic. If you need a little bit more help, let's actually look at the first example from the textbook here. So a local high school, 30% of the students who bring their lunch from home on one day will buy lunch from the canteen the next day. 50% of students who buy their lunch from the canteen on one day will bring their lunch from home the next day. Okay, pretty confusing, but let's try and put that into a transition matrix. That's showing the change over 2 days. So, or from one day to the next. So let's look at a transition matrix here that shows in the first column, let's say home. The first row, the first column, let's say home, and in the second, let's look at canteen. And we said that initially 30% of students who bring their lunch from home, so they bring their lunch from home, will buy their lunch in the canteen the next day. Okay, so we're talking about people that buy their lunch, bring their lunch from home the first day, will purchase their lunch in the canteen the next day. Okay, so 30%, which means 70% of those people that bring their lunch from home will also bring their lunch from home again the next day. Can you see how that row adds up to 100%? 100% of the people that are bringing their lunch from home will either bring it from home or they purchase from canteen the next day. 50% of the students who buy their lunch from the canteen one day will bring their lunch from home the next day. So we're saying they bring their lunch from the canteen one day, they'll bring their lunch from home the next, which is 50% here, which means if they purchase their lunch from the canteen one day, 50% of those will also purchase their lunch from the canteen the next day. Now, remember, transition matrix shows us those values as decimals. So the transition matrix is equal to 0.7, 0.3, 0.5, 0.5. Okay. There we go. Construct a transition matrix for the situation. Done. On Monday, 400 students from the school were surveyed. 243 bought their lunch from home, while the remainder bought their lunch from the canteen. Construct an initial state matrix for this situation. So my initial state matrix, there is going to be a total of 400 people represented, or students represented in that state matrix. It says that 243 bought their lunch from home. Now, it's important that I keep this in the first row, okay, the people from home in my state matrix. So 243 people bought them from home, which means the rest of the 400 students purchased their lunch from the canteen on Monday. Okay, so 400 initially, or students in total, take away 243, leaves me with 157 students who purchased lunch from the canteen. Okay, so now we'll have a transition matrix and a state matrix. What I'm going to do now is use those to determine how many students will buy their lunch at the canteen on Tuesday and Friday. Now, Tuesday is one day after Monday, okay? So initially on Monday, this is how many people bought their lunch from home, how many purchased from the canteen. So on Tuesday, which is one day later, it's going to be the initial state matrix times by the transition matrix, okay? So my graphics calculator, I can do that calculation. Again, I have similar to the example I went through previously, 1 by 2 state matrix, which is 243. In this case, my state matrix actually has an amount rather than a proportion, and my transition matrix again is also a 2 by 2. This time my values are 0.7, 0.3, and 0.5, 0.5. Okay, and that then tells me that 248.6 will bring their lunch from home on Tuesday, and 151.4 will bring their lunch, or will purchase their lunch from the canteen on Tuesday. The question says, how many students do you expect to buy their lunch at the canteen on Tuesday? Okay, so we're looking at this value here, but because we're talking about people in this context, we're actually talking about people, we can't leave it as a decimal. So I would expect 151 students to purchase their lunch from the canteen on Tuesday. How many would I expect to purchase their lunch from the canteen on Friday? Well, Friday is 4 days after Monday, okay? So to work that out, I'm going to do my initial state matrix multiplied by t to the power of 4, okay? Again, on my graphics calculator, I can do that calculation. Again, I'm just going to cheat here a little bit by raising this initial equation I did to the power of 4, which gives me 249.9 and 150.0, which means that on Friday I would expect 150 students to purchase their lunch from the canteen. Okay. Now, the last question is to find the steady state proportion of students who will buy their lunch at the canteen. Steady state proportion. So what we're going to do, rather than continue this this multiplication, this repetitive multiplication, we're going to just raise the transition matrix to a large number. Now, here you just got to, I guess, think of a large number. So for this one, what I'm going to do is I'm going to start by raising the transition matrix to the power of 10. In fact, so let's just do t to the power of 10 and see what that equals. So I'll pop in another 2 by 2. The transition matrix, as we said, was 0.7, 0.3, 0.5, 0.5. Raise that to the power of 10, and it gives us a transition matrix which is converging. You can see that people that bring their lunch from home after 10 days after Monday will be or 10 school days after Monday, I should say, 62.5%, and those purchasing from the canteen will be 37.5%. So that tells me that's probably going to be the steady state. If you want, you can just go and change that again to the power of 15, something like that. And again, perfect. Not much has really changed there at all. So I'm going to just put that as my steady state, which is, get that back up, 62.5% and 37.5%. So the question says, find the steady state proportion of students who will buy their lunch at the canteen. So obviously that first value tells us of the percentage of students that will be bringing it from home. And that second value, the second column, tells us the steady state proportion of students that will purchase their lunch from the canteen. So the answer is essentially 0.375 or 37.5% of students will purchase their lunch from the canteen as a general rule, okay? Unless something happens to change this transition matrix. You know, there might be a new item at the canteen. There might be an advertising campaign run by the canteen. The canteen might come under new management and have a complete overhaul. And they might redo it. So things can change. Therefore, the transition matrix may change. But based on the initial steady state matrix, based on the initial state matrix and the transition matrix, the steady state will look like this. Okay. So long video, guys. Hopefully it's helped. Thanks for watching. And yeah, I'll see you next time where we'll talk about, transition matrices again, where, there is a change to the transition matrix. Okay, so stay tuned for that one.